Let us look at the solutions for the questions posed in the PowerPoint slides for Seminar 1 and 2. First, we will look at the introduction to fluid mechanics, and one of the important questions that you are asked is how do you define internal flow, external flow, and open channel flow. Important words are highlighted: the flow of an unbounded fluid over a surface, such as a plate or wire or a pipe, is called external flow. Internal flow, however, is if the fluid is bounded by solid surfaces, that is, enclosed within the surface. The flow of liquids in pipe is called open channel flow if the pipe is partially filled with liquid and there is a free surface, such as the flow in waters, in rivers, in ditches, irrigation ditches. Okay, in our course, our flows are all internal flow or external flow. We will not look at open channel flow. Let's now move on to the next question. We are asked to define, in this case, incompressible and compressible flow, and discuss fluid compressibility. Now, in general, a fluid during which the density remains nearly constant is called incompressible flow. A flow in which the density varies significantly is called compressible flow. A fluid whose density is practically independent of pressure, such as a liquid, is commonly referred to as an incompressible flow. Although it is more proper to refer to incompressible flow. Notice the terms here: an incompressible flow, incompressible fluid. Okay, so we wouldn't like to say all fluids are incompressible. We would prefer to say incompressible flow, because in the case of air, below a speed of Mach 3 or 0.3, we can consider even air to be incompressible. Okay, so if you look at the next portion, the flow of a compressible fluid such as air does not necessarily need to be treated as compressible, since the density of a compressible fluid may still remain constant during flow, especially at low speeds. This is quite an important point. It turns out that the Mach number is the critical parameter to determine whether the flow of the gas can be approximate to incompressible flow. If Mach is less than about 0.3, the incompressible approximation yields results that are in error of less than 1 or a couple of percent. Now let's look at question 3. We are asked to define the no-slip condition. Okay, for the no-slip condition, a fluid in direct contact with a solid surface sticks to the surface, at the surface, and there is no slip. This is known as the no-slip condition, and this is due to the viscosity of the fluid. And it's important in the discussion to realize there's no such thing as a fluid with no viscosity. All fluids have viscosity, but in many cases we can say the viscosity is so small that we can neglect it. Now let's look at the next question. you are asked to discuss the boiling temperature of water and how it increases as pressure increases. Yes, it does increase. The saturation, the saturation temperature of a pure substance depends on its pressure. Okay, so the word saturation means if you give it enough energy, it cannot remain as a liquid or a solid, and in this case, in our case, it then changes phase. It is saturated, okay, in terms of energy, and a touch more energy will cause it to change phase. It increases with pressure. So the higher the pressure, generally the higher the saturation temperature. In everyday language, we call it boiling. In fact, it is easily seen by looking at the saturated property table. You can find it at the back of your textbook in one of the appendices. Okay, it might be interesting to note that the boiling temperature and saturation pressure at a given points are the same. Some people call it boiling temperature and some people call it saturation pressure. Now let's look at question number 10. You're supposed to consider the minimum pressure in a pump to avoid cavitation. So if you look at tables at 35 degrees, you will generally see that the saturation pressure is 5.63 kilopascal. What does it mean? It means that at 35 degrees centigrade, if the pressure drops to 5.63 kilopascals or 0.05 bar, okay, 0.0563 bar, you will have the condition when the water will change from liquid to gas. And remember, when we talk about the gaseous state of water, we refer to it as steam. To avoid cavitation, the pressure anywhere in the liquid should not be allowed to drop to the vapor or saturation pressure at a given temperature. Now, this is especially a problem in pumps, especially at the suction. Okay, so it's not a question of being able to pump how much fluid you want. If you try to drop the suction pressure to below the vapor pressure, then there will be boiling and there's going to be a lock in the pumping operation. So that will limit the lowest pressure you have in the pump. And it's especially wise to note that when you pump with increasing temperature, the risk of cavitation is greater at higher fluid temperatures. Now, this question which we are looking at now is in fact in the third edition. It was left out in the fourth edition, but I thought it's an interesting problem to demonstrate to you. Here you are told the Mach number of an aircraft and the speed of sound are to be determined at two specific temperatures. The first at 27 degrees and the next at 727 degrees. We are going to assume that air is an ideal gas. When you do thermodynamics, you will learn more about what we call the specific heats at room temperature. Why are they important? Because their ratio gives you the way it's called the index of compression or expansion. Okay, and in this case, we call it K or gamma. Okay. Some people call it K, some people call it gamma. It's the ratio of the two specific heats. Okay, here I have spelled out the derivation or the term, the definition of gamma or K, which you will learn in thermodynamics. Is a ratio of what we call the specific heats. Now, to calculate the speed of sound in air, we use this formula. The speed of sound is equal to the square root of K, which is this, multiplied by the gas constant times the temperature in Kelvin. So for air, K or gamma is 1.4. The gas constant is 0.287, and we have to convert 27 degrees into K, which is 27 plus 273. Okay, I've written it out in this way, where capital T is the temperature in Kelvin and small t is the temperature in centigrade. So that's why your 27 degrees centigrade becomes 300. Then you do conversion, because you have to reduce all your units to comparable numbers, and you get the final answer as 347 meters per second. So our aircraft is traveling at 240 divided by the Mach number 1347, we get a 0.692 Mach number. Now, if we do the same thing at 1000 K, which is 727 degrees centigrade, okay, which we plug in here, plus 273, that gives us 1000. Crunch the numbers and we get the speed of sound as 634. So when the temperature increases, it is interesting to note that the Mach number decreases. Okay, so in the discussion, there's an interesting point to note that a constant Mach number does not necessarily indicate constant speed. The Mach number of a rocket, for example, will be increasing even if it ascends at a constant speed. Okay, as you can notice that as the rocket travels further and further up into the atmosphere and stratosphere, the temperature drops. Also, the specific heat ratio changes with temperature, and the accuracy of the result at 1000 degrees K can be improved by using new specific heat values at that temperature. Okay, and then you would give a more accurate calculation of Mach number. Instead of 1.4, it is in fact 1.386. Next, we look at the question 9-35, and here you have a two-cylinder arrangement where the inner cylinder rotates and the outer cylinder is stationary. Okay, so we make certain assumptions. The inner cylinder is completely submerged in oil. The viscosity effects of the ends of the cylinder are negligible, and the fluid is Newtonian. If we substitute the given values, the viscosity of the fluid can be determined by this formula. If you recall, this formula is available in your PowerPoint slides. The only difference is the torque is the subject of the formula. In this case, the dynamic viscosity is what we want to find. So we know the torque, we know the thickness of the film, okay, and then 4, we know pi squared, we know r is the radius of the inner cylinder, 75 millimeter or 0.075, we have to change it to SI units, which is in meters. 300 revolutions per minute is 300 over 60 revolutions per second. And the length of the cylinder, if we look at the cylinder into the paper, the length L is 0.75. Okay, so this is a viscosity value at the temperature that existed during the experiment. Viscosity is a strong function of temperature, and the values are significantly different at different temperature. It will be an interesting exercise for you to derive this formula from first principles. In fact, I have provided you a derivation which we will see later on.